Hello class, let's talk about limiting reagents and combustion reactions. If you start with 15 moles of each reactant, which would be the limiting reagent, how many moles of uranium hexafluoride could be produced? Normally the limiting reagent is the reactant that is used up completely. The one you have excess is called excess reagent. So let's look at this equation. First, make sure it is balanced. It is balanced. So you have 15 moles of uranium, 15 moles of fluorine. So what we are going to do is we pick one reactant and see how much of the other you need. Let's pick uranium. And when you look at the stoichiometric coefficients, you see 1 mole of uranium reacts with 3 moles of fluorine. And we have 15 moles of uranium. We start from there and find out how much of fluorine we need to react with these 15 moles of uranium. We start with 15 moles of uranium. And we know 1 mole of uranium needs to react with 3 moles of fluorine. And the number of fluorines you need 45. However, we have just 15 moles. So that means limiting reagent is fluorine. How many moles of uranium hexafluoride could be produced? The number of moles that can be produced, we are going to use the number of moles of limiting reagent. We know it is fluorine. And by the stoichiometric coefficient, we know 3 moles of fluorine produce 1 mole of uranium hexafluoride. We have only 15 moles of fluorine. So we start from there. 15 moles of fluorine times, we know 3 moles of fluorine are required to make 1 mole of uranium hexafluoride moles. So the answer is 5 uranium hexafluorides. If you start with 15 grams of each reactant, which would be the limiting reagent? So we start with 15 grams of each. And we know 1 mole of uranium reacts with 3 moles of fluorine. And these are the molar masses of uranium and fluorine respectively. So when you have given the information in mass, you have to convert this to moles first. And we are going to find the number of moles of uranium first. We start with 15 grams and we know 1 mole of uranium weighs 238.0 grams. You can see units to units cancel out. This part gives you the number of moles of uranium in 15 grams. Now we have to find out the number of fluorines required to react with this 15 gram. For that, we are going to use the stoichiometric relationship. We know 1 mole of uranium reacts with 3 moles of fluorine. Now we have in this part the number of fluorine moles required for the reaction. Now we are going to convert this number of moles to grams. For that, we are going to use the molar mass of fluorine. We know 1 mole of fluorine weighs 38.0 grams. And then the answer is 7.18 grams fluorine. So what does this mean is 15 grams of uranium requires only 7.18 grams of fluorine. But we have 15 grams, that means we have excess. So fluorine is your excess reagent, uranium is your limiting reagent. How many grams of uranium hexafluoride could be produced? For that, we take the limiting reagent, which is uranium. So we need to find out the molar mass of uranium hexafluoride as well. So we do the dimensional analysis. We take the limiting reagent, 15 grams of uranium, and we are going to convert it to the moles. For that, we are going to use the molar mass of uranium. Then we are going to find the number of moles of uranium hexafluoride produced. For that, we are going to use the stoichiometric relationship. 1 mole of uranium produces 1 mole of uranium hexafluoride. And then we are going to end up with number of moles of uranium hexafluoride. Next step is to convert it to the mass. We know 1 mole of uranium hexafluoride weighs 352 grams. You can see all the units cancel out and the final answer should be in grams. So this is the maximum product you can get when you react with 15 grams of uranium. So we call this the theoretical yield. If 100 grams of uranium was reacted with 50 grams of fluorine, what would be the theoretical yield of uranium hexafluoride? To do this question, first we have to find out which one is the limiting. So we have 100 grams of uranium, 50 grams of fluorine. We pick one, let's say we pick uranium. We start with 100 grams and we are going to convert it to the moles. For that, we are going to use the molar mass of uranium. And then we are going to use the stoichiometric relationship. 1 mole of uranium is required to react with 3 moles of fluorine. And here in this fraction, you can get the number of fluorine moles that needed to react with 100 grams of uranium. So next step is we are going to convert it to the grams. So for that, we are going to use the molar mass of fluorine. The answer is 47.9 grams of fluorine. That means to react with 100 grams of uranium, we need only 47.9 grams of fluorine. However, we have 50 grams. That means we have excess of fluorine. Fluorine is your excess and uranium is your limiting. To calculate theoretical yield, we are going to use the number of moles of uranium. So we start with 100 grams and we convert it to the number of moles using the molar mass. And you see 1 mole of uranium produce 1 mole of uranium hexafluoride. And then we convert it to the grams using the molar mass of uranium hexafluoride. So the theoretical yield of this reaction when you start with 100 grams is 147.9 grams. A generalized way to show how aluminum is extracted from its ore is shown below. This is the equation you are going to use. How many grams of carbon are required to produce this much of aluminum? And it's given in kilograms. So you need to figure out the information you are going to need. So by looking at the stoichiometric ratio, you can see 3 moles of carbon produce 4 moles of aluminum. Now the question is in between carbon and aluminum. We need to get the molar mass of carbon and the molar mass of aluminum. Also the question is in kilograms. So we are going to need the 100 grams to 1 kilogram conversion factor as well. So let's do the dimensional analysis. First, we are going to use 3 times 10 to the 6 kilograms of aluminum and we are going to convert it to the grams. So we use 1 kilogram of aluminum equals 1000 grams of aluminum. You can see kilograms and kilograms cancel out. Now we have the weight in grams. Now we need to convert these grams into moles. For that, we are going to use the molar mass of aluminum. We know 1 mole of aluminum weighs 26.98 grams. Now we are going to find out the number of moles of carbon required to make this much of aluminum. For that, we are going to use the stoichiometric relationship. We know 4 moles of aluminum requires 3 moles of carbon. Now we have the number of moles of carbon required to produce this much of kilogram. Now we need to find the grams of carbon. For that, we are going to use the molar mass. So the answer to your question is 1.5 times 10 to the 9 carbon grams. How many grams of carbon dioxide are produced from the reaction of 873 grams of aluminum oxide? The equation is given and we are going to start with this many of grams and we are going to find how many grams of carbon dioxide are produced. For that, we are going to use the stoichiometric relationship between aluminum oxide and carbon dioxide. We know if we react 2 moles of aluminum oxide, we are going to produce 3 moles of carbon dioxide. And also we need the molar mass of aluminum oxide and the molar mass of carbon dioxide. So we start with 873 grams of aluminum oxide and we are going to convert it to the number of moles using the molar mass of aluminum oxide. We know 1 mole of aluminum oxide weighs 1.96 grams. Next, we are going to find the number of moles of carbon dioxide produced. To that, we are going to use the stoichiometric relationship. 2 moles of aluminum oxide produce 3 moles of carbon dioxide. You can see these units cancel out each other and we are going to end up with moles of carbon dioxide for this part. Now we have moles of carbon dioxide. Now we are going to convert it to grams of carbon dioxide. So we use the molar mass in this sort of fraction in such a way that it can cancel out mole to mole carbon dioxide and we are going to end up with gram carbon dioxide. The answer for this question is 565 grams. If you start with 525 grams of aluminum oxide and 842 grams of carbon, which reactant is the limiting reagent? So we are going to pick one reactant first and then to see how much of the other reactant is needed. So when you look at the stoichiometric coefficient, you see 2 moles of aluminum oxide reacts with 3 moles of carbon. We are going to use that information and then we are going to use the molar mass of aluminum oxide and the molar mass of carbon. So we pick aluminum oxide and we start with 525 grams. So we are going to convert this to number of moles using the molar mass of aluminum oxide and then we are going to find out how many moles of carbon we need by using the stoichiometric relationship. 2 moles of aluminum oxide needs 3 moles of carbon. You see all the units cancel out and we are going to end up with number of moles of carbon and we are going to convert it to the grams using the molar mass. So the answer to this question is 92.76 grams of carbon are needed to react with 525 grams of aluminum oxide. However, we have 842 grams of carbon. That means we have excess, which makes the aluminum oxide to be limiting. Let's look at the combustion reactions. A hydrocarbon underwent combustion to produce 0.379 grams of carbon dioxide and 0.1035 grams of water. Determine the empirical formula of this compound. So the equation is given. We call these equations combustion reactions because oxygen is going to react with the substance. So to find the empirical formula, we need to calculate the number of moles of carbon in carbon dioxide and number of moles of hydrogen in water. So the grams are given that it produced 0.37 grams of carbon dioxide and 0.1035 grams of water. So we are going to find out the stoichiometric relationship, and when you take the carbon dioxide molecule, you see one carbon dioxide molecule has one carbon atom. That means same goes to as the moles. 1 mole of carbon dioxide has 1 mole of carbon. Also, we need the molar mass of carbon dioxide. When you look at water, you can see 1 mole of water has 2 moles of hydrogen. Also, we need the molar mass of water. So, we are going to find out the number of moles of carbon first. So, we have the mass of carbon dioxide. Remember, you have given the mass of carbon dioxide. So we start from there, 0.379 grams carbon dioxide, and we are going to use the molar mass to find the number of moles of carbon dioxide first. And then we are going to use the stoichiometric relationship to find out the number of moles of carbon. You can see all the units cancel out and we have the number of moles of carbon. We do the same to the water. We have the mass of water here and we use the molar mass to convert this to number of moles of water. And then we are going to find out the number of moles of hydrogen by using this stoichiometric relationship. Now we have moles of carbon and moles of hydrogen. So we get these two ratios by dividing the both numbers by the smallest number. Okay, and you will see it's 1 to 1.34. When you have a number which is closer to full integer, we are going to multiply it to get a full integer. So we are going to multiply this by 3 and to get C3H4. This is your empirical formula. 1 gram of sample of a compound containing carbon, hydrogen and oxygen underwent combustion, producing 1.32 grams of carbon dioxide and 0.839 grams of water. Determine the empirical formula of this compound. Now remember your original compound weighs 1 gram and you have given the mass of carbon dioxide and water. From this information, we can find the number of moles of carbon and number of moles of hydrogen. So we have to figure out a way to use this mass to find the number of moles of oxygen. So we know now 1 mole of carbon dioxide has 1 mole of carbon and this is the molar mass of carbon dioxide. 1 mole of water has 2 moles of hydrogen and also you are going to use the molar mass of water. First we are going to find out the number of moles of carbon. For that, we are going to use the mass here, 1.3 grams of carbon dioxide, and we are going to use the molar mass, and you are going to get the number of moles of carbon dioxide. So, 1 mole of carbon dioxide has 1 mole of carbon. So, the number of moles of carbon are 0.03. Next, we are going to do the same thing to water and going to find out the number of moles of water. Now we know the mass of this compound. So if we find out the mass of carbon and the mass of hydrogen, we can find out the mass of oxygen. To find the mass of carbon, we are going to start with the number of moles. We know we have 0.03 moles of carbon and 1 mole of carbon weighs 12.01 grams. So we know the mass of carbon. We do the same thing to hydrogen and find the mass of hydrogen. So we are going to subtract these two numbers by 1 because your mass of the sample is 1 gram and you get the mass of oxygen. Now you have the mass of oxygen. Now you can convert it to the number of moles. To that you are going to use the molar mass of oxygen. You have 0.034. Now we take the ratios, mole ratios of now we take the mole ratios of carbon, hydrogen and oxygen. So we are going to divide it by the smallest number and you will see 1.1, 2.6 to 1 and to get full integers we are going to multiply it by 2. So your empirical formula is this. This is the end of this session and if you have further questions please let me know. Thank you.